So this is problem 83 from chapter 23. So in this problem, they are providing you with some context about the configuration that they want you to investigate. But the context is not really that important, so it's about the Geiger counter and so on and so forth. But the important thing is the geometry that they provide. And the geometry is, there's some cylindrical rod, and around this there is a cylindrical shell. Okay? And these are both very long. Okay? The outside cylindrical shell has a linear charge density, charge per unit length, of minus lambda, whereas the inner one has a linear charge density of lambda. And they're asking you to find the electric field between this wire, this thin one, and the cylindrical shell, and then calculate to show that the potential difference is given by some expression that involves logarithms. So to make things a little bit more clear, perhaps I'm going to provide the cross section for this one. Okay, and I'll make the inner wire a little bit thicker. Typically, in a Geiger counter, of course, this is going to be much smaller than the outer radius. And the inner radius is given by R1. The outer radius is given by R2. Okay? So the first part is to finding the electric field in between these two. Okay. And of course, we are going to assume that we are far from the edges. It's given that these are long structures, which means that we can just assume cylindrical symmetry. Now, in fact, we solved this problem already. The electric field is going to be exactly the same as that of a thin charged rod. The reason being that this outer cylinder doesn't enter our calculations, right? So if I draw a Gaussian surface, a cylindrical Gaussian surface around the inner rod, with some radius r, okay, and this r is going to be exactly what we want in between these two radii, then everything I said for the single charged rod is going to apply to this problem, right? Because the enclosed charge is the same and the cylindrical symmetry is still preserved, so this cylindrical shell around, because it's coaxial with the thin rod, doesn't change anything, right? The cylindrical symmetry is still going to be there, and by cylindrical symmetry what I mean is that translational symmetry along the axis and rotational symmetry around the axis. The presence of this doesn't destroy that, so everything we said for that problem is going to be applicable, right? So we can just copy the electric field magnitude from that one, and that was lambda over 2 pi epsilon naught r. Okay? And if you want to give the direction, you can just say this is radially outward, the radial vector being this way. Let's just draw it this way. Right. Something like this. Okay, so then they are asking for the potential difference VA minus VB. Now, this is, of course, an application of our formula relationship between the electric field and the potential difference. And this is going to be our integral of E dot dl, this one. Okay? And to make things a little bit more concrete, I'm going to draw a coordinate system. Again, I will use this one. Okay? So let's say that this is my x, this is my y, and I will be integrating from, I'm going from B to A, so I should start from here. I'll be integrating from here to here. Okay? So this is my, actually they call this RB and RA. I should not change notation this way, so this is RB, and this is RA. So I'm going to start from this point and end up at this point. All right, so because it's on the x-axis, this actually simplifies. My electric field and my path are parallel to each other, so I can just write this down as the minus sign x equals RB to x equals RA, E dx. Okay? And this E, the magnitude is just given by this, so this is going to be from RB the minus sign to RA, lambda over 4 pi epsilon naught x dx. So this lambda, sorry, 2 pi epsilon naught. That lambda 2 pi epsilon naught can be taken out of the integral. It's just a constant, and the integral of dx by x is just a logarithm. Right? So this becomes minus lambda over 2 pi epsilon naught logarithm of x from Rb to Ra. Okay? And then this is going to be a logarithm of Rb minus logarithm of Ra. If I take this negative sign, then it's going to flip those around. Sorry, this is going to be logarithm of Ra minus logarithm of Rb. With the negative sign, it's going to be flipped around. I misspoke. 2 pi epsilon naught. Now this is going to be ln Rb minus ln Ra. And this is the difference of logarithms. The difference of logarithms is the logarithm of ratios. So this will be lambda over 2 pi epsilon naught ln Rb over Ra. Okay? Which is compatible with the expression given in the book. Right. So is there anything? So there's one confusing issue here that going from here to here, and I actually plan to address that in another separate video. But it's not perhaps obvious to you that why this is not going to be minus dx, because we are moving in that direction. That minusness, the sign of that line element, is actually taken care of by the integral limits. Okay, you don't need to take care of that. In fact, you should not take that into account over there. But as I said, I'm going to address this in more detail in another video.